Welcome everyone to the Green Chemistry Education Webinar Series hosted by the Green Chemistry Commitment. My name is Amy Cannon and I'm the Executive Director of Beyond Benign, nonprofit dedicated to green chemistry education. This webinar series, as I explain each time in these webinars, they're designed to highlight relevant topics in green chemistry education for faculty and students who are looking to adopt green chemistry in their courses and programs. So as a reminder today, we are broadcasting live and recording the session. So all attendees are in listen-only mode and all lines are muted. So if you have a question, then just type it right in there into that question chat box on your control panel, and we will have a look at them and we'll respond to as many questions as we can after Dr. Henry's presentation today. And the presentation, the recording will be posted on the link that you see in the welcome box and on this slide here as well. And the supporting documents, such as the presentation slides, are also posted at that link as well. And we've also, for this time, are figuring out our go-to webinar system here, and have also attached the slides as a handout. So you should be able to download that directly from your control panel as well. So for those of you who like to participate in social media, please feel free to live tweet or join in the conversation about this topic or any of our other events as well. Here are some of our Twitter handles and hashtags and all of that. And you can also connect with us directly through Facebook. I believe we also have the University of Colorado Boulder Green Labs program students and faculty joining us out there. So another shout out to them for joining. Fantastic group out there. So this webinar is being brought to you as part of the Green Chemistry Commitment Program, which I always just mentioned. It's a consortium program aimed at uniting the green chemistry community and bringing more green chemistry to departments. If you're interested in learning more about this program, feel free to connect directly to our website or send me an email directly. As part of the webinar series, we always give away a green chemistry book at the conclusion of each webinar, and then we randomly select a winner from our list of attendees at the end, and we'll get your contact information and send it right out to you. So today we do have Dr. Sally Henry's new lab manual from last year from CRC Press, which is pictured here on the right of this slide. So if you do have this particular topic of interest, we'd be happy to send that out to you too. So now I'd like to introduce our speaker, Dr. Sally Henry. Sally Henry is a professor of chemistry at Union University in Jackson, Tennessee, and has been in chemical education for over 16 years. Dr. Henry has taught various courses in laboratories, including fundamentals of chemistry, general chemistry, organic, inorganic, advanced organic, environmental chemistry. She's also involved in mentoring undergraduate research students in chemical education and dendrimer research. Dr. Henry previously worked as a junior research chemist for Phelps Dodge Corporation, a plant chemist for Mount Pleasant Chemical Company, and materials lab supervisor, process engineer for the Whirlpool Corporation. While working in industry, she contributed to various environmentally related projects. And she's also the author of a new green chemistry laboratory manual for general chemistry published last year, which I just mentioned. So with that, Sally today is going to be talking to us about using greener labs in high school and general chemistry courses. And we're very excited to have her present here. And I am going to hand the controls right over to you now, Sally, so you should see that prompt come up. And we can see your screen.
Thank you very much, Amy, for inviting me to present our work on using greener labs in high school and general chemistry courses. And thank you, everyone who has decided to join this webinar. I wanted to just start off and just kind of talk about the advantages of green chemistry, as I'm sure most of you are aware of, but some of our thinking. And in fact, what I'm going to do in this webinar is I'm going to carry you through kind of a history of how we've got where we're at and let you know some of what we've been doing then. Obviously, for green chemistry, one of the main advantages in the high school laboratory setting as well as in general chemistry is that the students will be dealing with much safer materials. I realize that when high school teachers have large classroom sizes and they have hazardous materials that they have to do labs with, that they tend to not want to do that many. And so if they have safer materials and experiments that the students could actually find fun and hopefully at least inviting and interesting, we're hoping that it will encourage them to be willing to do even more experiments, because after all, chemistry is an experimental science, and one of the best ways to get students involved and excited about chemistry is through doing chemistry experiments. It also will help with students learning about sustainability and being more environmentally friendly. And teachers have enough to do, as do instructors and stockroom managers. So if we can make labs that require a much more simple cleanup of waste, it will save a lot of time to from their already busy schedules. And a main thing is the no costly disposal of hazardous waste. And in these experiments that we developed, and myself and my research students developed, we also like to use materials the students can easily relate to. So as far as the savings, I just did this briefly, didn't spend without really spending a lot of time on it, but I wanted to point out that if we use there's 3.767 million U.S. public high school 10th grade students, or there was in 2014, assuming that they pretty much all took chemistry or a physical science course where there was heavy metal waste. If we could save just an average of 1 gram of heavy metal waste per student, that would be 4.15 tons per year. And that might not seem like a lot from an industrial standard, but when you consider that each one of these schools, especially the high schools, as they're disposing of it, they have small amounts, and it costs a tremendous amount of money to dispose of just a very small amount of a hazardous substance. So this can be significant savings, and it can also put money back into the education system, and where it can do much more good than just getting rid of heavy waste. Now I'm going to go more into our research. I began this research with 2 research students, Casey and Ruth, and we began to look into developing a green chemistry laboratory manual in 2002. At Union, our students are required to do an undergraduate research project, and they were both wanting to become high school chemistry teachers. They came to me and asked me if they could do a project with me that would be really related to their profession that they were choosing. And so what we looked at was a manual, and I had just been at the ACS National Spring Meeting and heard Mary Kirchhoff talk about green chemistry, mostly more towards organic, using greener organic experiments. And I thought, well, why not high school? And Casey and Ruth were excited about it, as was I. And so we began to look into developing a greener high school chemistry manual. Now, I want to point out that at this point, our focus was just to provide greener experiments that covered the traditional topics. At this point, our thinking was not to actually teach students about green chemistry. In that initial work, they did a fantastic job, and they developed 19 experiments. And we printed out a student's manual, and they presented it at the next ACS national meeting and at some other regional meetings. The criteria that they chose for the labs was 45 minutes or less, and they wanted that so that if someone was on a traditional scheduling, that they could do it within a typical class period. But if they were on block scheduling, then they could do both the pre-lab, the lab, and the post-lab all on the same day. And our other goals were, of course, to reduce toxic organic waste along with hazardous waste. Cost, of course, was very important. We realized that teachers at the high school level, especially around here, do not have an excess of funds to spend on labs. At this time, we also were very concerned about re-emphasizing the material learned in class, and we wanted something that would be relational and have the students thinking, inquiry-based learning that's appropriate for the high school students. Of course, we wanted to interest them, and we really wanted to also use and teach the basic lab techniques so that they would learn those as well. Well, at that point, after this was done, we had a tremendous amount of interest, but didn't really know where to go from there. And fortunately, the Tennessee Department of Environment and Conservation, also called TDEC, was doing a twofold project. And the first part of that project was to remove hazardous waste and materials from high schools across the region. Now, I'm sure that Tennessee isn't the only place where there's been industries and they have donated old chemicals to them that they were no longer going to high schools that they were no longer going to be using. And also, over the years, other experiments would be developed and there would be additional waste, heavy hazardous waste brought in. And then they were just stuck with all of this. And one of my colleagues, Marlon Newhouse, Dr. Marlon Newhouse, she was working with them because she works with a lot of the area's high schools and schools in general around here. And so she was in contact with them and trying to help with this project. And at the time, they said, well, our second part of this project is to prevent future acquisition of the hazardous materials. And she very kindly said, well, that they should talk to me about green chemistry. It was because of their involvement that got us, that we continued on this, and we developed a supplement, and they asked us to develop a supplementary teacher's manual and also to post 3 of the labs on their website. And this is just the website, and they did a great job of it. I had another student at that time, Kimberly Lindsay, who was wanting to work on this project. And so she started out to do what TDEC had asked us to, the additional work to do. And she had quite a job in front of her. As far as she went out and started talking to teachers and asking them what their suggestions were. And what she found from talking to teachers is that they wanted a few additional concepts covered. They wanted some pre-lab questions associated with the introduction and the procedure. In the original labs, there were no pre-lab questions. Wanted some safety reminders so the students would see it and it would be bolded, along with helpful hints and cautions, and also some additional figures of the different apparatuses. Then in the teacher's manual, they suggested answers to the pre-lab and post-lab questions in the text, not in an appendix, and they wanted a unified materials section with supplies indexed along with large margins for note-taking. Well, she took all those into account when she went ahead and developed out a few additional labs and also the teacher's manual. We worked together on that and came up with the additional labs. And so here are the experimental concepts in that our very first green chemistry lab manual for introductory high school covers. And as you can see, most of these are pretty typical. There's nothing, we remember our goal was to teach the traditional topics, and yet at this point to do it with greener materials. Here's a list of the table of contents, and again, we were trying to make things that students could relate to. And so we have things like caffeine and junk food, hand warmers and cold packs, fireworks, laser pointers, sugar and salt, slime and silly putty. And as you can tell, most high school students can relate to most of these things. We also were looking at candy and a lot of other type things that we tried to keep it where students would be interested. This is just showing how we incorporated the helpful hints and the cautions into the procedures. In the teacher's manual, we also have some helpful hints for the teachers off to the side. Sorry. And here's the pre-lab questions, again, not in the appendix, but made in the format so that they're looking at it. When they're grading, they can see what they're looking at, what the students have, and more easily grade. And this is what the preparation materials table looked like. We have the general supplies section, the laboratory equipment, and the chemicals. And within the chemicals, we actually talk about how the preparation would have to be done so that the teachers don't have to spend time doing the calculations. Again, trying to make it as user-friendly for the teachers as possible. Once we got done with this, we decided to put it out there for teachers who were interested so that they could purchase for themselves a copy. And what we provided was a Word document of both this and the teacher's manual, so that teachers could change it as they needed to for what the types of equipment they had, maybe change a few of the questions, those kind of things. It's very frustrating for students if it says for them to use a 150 ml beaker and their lab drawer only contains a 100 ml beaker and a 250 ml beaker. So this way, those kind of issues could be addressed before the students actually tried to do the lab. So I just want to now give a couple of examples of the labs that are in this manual. The first one is sugar or salt, and it deals with ionic and covalent bonding. Again, we were using sugar and salt because these are two chemicals that students can relate to. And if you take a tablespoon of sugar and put it next to a tablespoon of salt, there's really just no differences that you're going to be able to see, but yet they have very, very different properties, and of course one is, the salt is ionic and the sugar is covalently bonded. So the objectives were for students to be able, through this exercise, to define and learn about ionic and covalent bonding and know the differences between them. And they want to see that there's a link in the physical properties between ionic and covalent bonding, and also to be able to characterize the type of bonding that sugar had and also salt. This is a two-part procedure. In part one, we use a simple anodizing type of apparatus where the students will see bubbles forming if in an ionic solution, and they will not see that in a covalently bonded solution. It takes very little time, and they'll see a good stream of bubbles. In the second part, we are also introducing using a Bunsen burner. In this one, they're looking for melting temperatures. Again, one of our goals in this was to teach them typical or traditional laboratory techniques, and of course, a Bunsen burner is one of those. And so they start with putting a small amount of sugar in the bottom of a test tube. They place it over a flame at several inches above the flame, and then after a little while bring it down until they see it start to melt. They also do that with the salt, and of course what they're going to see is at the very beginning with the sugar is it will melt higher above the flame and it will melt very quickly, where with the salt they have to get into the hotter part of the flame, and then it takes quite a while in order to get any kind of melting to occur. So just reinforcing that they have different physical properties. The second procedure that I'd like to talk about was on the periodic table, its trends and uses. And in this one, we're wanting the students to understand the periodic table and how we can actually learn about the relationships between the things within the elements within the different groups. And so we want them to relate the characteristics within a group. And then also in this one, we're beginning to introduce the idea of moles and reactions. And this is just showing an overview of it. we have the students first blow up the balloons, and it was surprising to me how many students really didn't know how to blow the balloons up very well. But that's something that they seem to enjoy, is trying to get the balloons blown up at the very beginning. And then they put equal molar amounts of lithium, sodium, potassium carbonates in 3 different balloons. They're attached to flasks that are containing a certain volume, a pre-designated volume of 1 molar hydrochloric acid. Now, originally we had done this lab with much stronger hydrochloric acid, but for safety's sake, we wanted to make it as dilute as we possibly could, and found that the 1 molar would work, and we could get enough in it and still have it within the flask and the smaller flasks that the balloons would fit on. As you can see within it, and on this picture that's shown here, they blow up pretty close to the same size. Of course, this depends on whether or not there's a hole in one of the balloons. We've had that happen, or if for some reason it's leaking around the edges. But for the most part, they'll get pretty close to the same blowing up of the balloons. We then have them take equal gram amounts of the lithium carbonate and the potassium carbonate and compare those two. And of course, now they will blow up different amounts. And so this way they can start to understand. We haven't really gone into the calculations with them yet on this, but they can start to understand that moles are different than grams. And of course, in this, carbon dioxide is given off as the gas. At this time, we pretty much finished that project. Of course, we were still having it out there and giving in-services and workshops to teachers on it, and making corrections as we were giving the workshops and finding and improvements. But right around that time, our administration was looking at contingency plans if there was some kind of a major disaster that would cause a campus shutdown. And one of the things they were very concerned about were what would happen as far as the chemistry labs, what they would do and how this could be accommodated. And so I was teaching the introductory chemistry at the time, and so the dean's office had asked me to give some ideas. And at that time, I also had another student, Lydia, who wanted to work on this. And we started looking at, what about a web-based course? And also later on, I had 2 other students, Tiffany and Jessica, who wanted to work on homeschool, developing for a homeschool manual. They worked on it and came up with these manuals. Lydia came up with a way that we could put all of the chemicals together in a box or in a plastic container and get it to students if we had some kind of a disaster. And Jessica and Tiffany put together a materials list for parents that they could put together for their homeschool students or their kids that they were homeschooling. And the problem is that while we were doing this, we realized that if we had a major disaster, how would we even get back to the chemistry department and our stockroom to put this together? And we also realized that homeschool parents it would be pretty difficult for them to gather everything that they would need to do. Good thing is that Tiffany and G, they were able to incorporate in some activities for younger children, and they did Lydia and Tiffany and G did. Jessica did a fantastic job trying to see how this could be done. Fortunately, at that time, Linda Wang was putting together an article called Science of Homeschooling, and she had heard about our work, and she came and interviewed me. And through just a very short paragraph on that article, eScience Lab saw it, and they contacted us, and this was a good way of dealing with the gathering of the materials for these types of learning situations. So eScience at the time had biology and physical science, and they wanted to branch into chemistry as far as for web-based or homeschool materials. And so we worked with them to initially develop the introductory chemistry kit and then later on the general chemistry kit, as you can see down here. Some other things that we did during that time is we developed a introductory high school lab manual that we used here at Union. We never did make that one available. We took many of the labs that were in the introductory high school, but we combined them and increased the level of rigor that was needed to do these labs. And they worked quite well here at Union, but as I said, we never did make those available to the public, and that is a goal of mine to someday actually do this. Well, time went on for a little bit, and during that time we had people asking us to develop, high school teachers asking us to go ahead and develop an AP lab manual. We started thinking about it. And during that time, as we were looking at doing this, I also noticed that more and more textbooks were putting the 12 principles of green chemistry, as I've shown here. And it would show all of them. It'd have a brief description, and they still do this, have a brief description as far as what the 12 principles of green chemistry are about, and usually a real-world example. And I was very happy to see that it was starting to reach into the textbooks, but also realized that the students, they would read it and they'd say, well, this is great, but it was more of a very superficial understanding. And as I went to workshops in the on green chemistry, I was hearing more and more that educational materials were needed that actually taught the students how to utilize green chemistry. As I was listening to many of these presentations, realized that for the most part, what was done is they were showing that they were teaching the green chemistry mainly in organic courses, but also with some other classes where they found that they could teach it best in a laboratory setting. So in 2011, we began to develop an undergraduate research project, and that was focused now on developing a green chemistry laboratory manual for the AP and general chemistry students. It eventually was published by CRC Press of Taylor and Francis Group, and it was several of the labs were also used by eScience Lab, and they were able from the labs that we gave them to adapt them in order to make a general chemistry web kit for a web-based course, or also an AP, general AP or AP chemistry. So a question I've been asked is why target general and AP chemistry? And the reason I wanted to target that, besides having AP chemistry teachers asking me to develop it, is that at this level of chemistry is taken by most science and engineering students. Now, many of the science and engineering students in other disciplines besides chemistry, they might not go on past this level, and so this is a good level to really introduce green chemistry. It's their foundational chemistry course, and so what better place than a foundational chemistry course to get students to start learning how to utilize green chemistry principles, and just in general to think green. And from this, then they can continue to build on it. So our goals were very similar to, the first goals were very similar to what we had in our first manuals for introductory high school. We wanted to reduce or eliminate hazardous chemicals. We still wanted to teach the traditional material and the basic laboratory techniques that are taught in those particular courses, We still wanted to incorporate the relational and inquiry-based learning. And of course, we wanted to interest the typical general or AP chemistry student. But now we had some added goals. These last two goals, we wanted to educate students on how to utilize green chemistry and to impart a vision to students to think green. Now the last goal, I have to admit, was the hardest one, and I'll address how we did this in the next few slides. So how did we do this? How did we educate students about green chemistry? Well, we started with the basics in the introductory material. We showed them what green chemistry was. We emphasized the fact that it's to reduce or eliminate, that you don't necessarily eliminate all hazards, but as long as we can reduce them, that we've made progress. We also tried to get them to understand that this is something that should be, that what we're wanting is for people to start thinking about it at the start of a project. As they are designing a new process or a new product, start looking at it as how can we design this so that it is the greenest it can possibly be. At this time, we also introduced the 12 principles of green chemistry, along with emphasized safety and include equipment and common laboratory practices. So that's just the introductory material. As far as the experiments go, we have a very consistent format. The first 7 of them or 8 of them are pretty typical for most labs. We have an introduction, objectives, pre-lab questions, procedure, data, observation, calculations, analysis. In other words, nothing that is very different than what you're used to. It's the last 2 that we've made some changes or added in. One is called a Think Green section, and the other is the Presidential Green Chemistry Challenge. Here are the experimental concepts that, as you can tell, are pretty typical for AP or general chemistry. Again, we wanted to teach the traditional concepts, and as you look through these, I believe you'll recognize that these are the ones that are typically taught in the first year of college chemistry and also in AP. And we had a goal, and that is to educate students on how to utilize green chemistry. And we do this throughout. Our introductory material, again, integrates the green chemistry concepts. Our introductory material, I should say, for each of the labs, it's going to not only teach the typical traditional material, but we actually strive to integrate green chemistry concepts and applications within that introductory material as well. The pre-lab, the questions in the pre-lab, they include green chemistry topics quite frequently. This would include things such as atom economy. And our last question always asks the students to determine the hazards. We want them to start thinking about the hazards, not just have it briefly told to them or where they read it, but we want them to have to dig in and actually take the time to look through the material and say, okay, I'm using boiling hot water here. I do not want to touch that beaker, and those types of things. I have long hair, and I'm going to be using a Bunsen burner. I need to tie my hair up. We want them to really see those hazards. We also want them to get used to looking up chemical hazards and seeing how to understand and recognize the chemicals that are very hazardous compared to ones that are not nearly as hazardous. In the Think Green section, we have the students then often compare the procedure that they used, which of course is a greener procedure than usually, not always, but usually a much greener procedure than is used in the traditional ones. And then at times we ask them just to try to develop a greener method. And if there's time and resources available, test their ideas. This slide is just to show how some of the green chemistry principles are integrated within the lab. I'm not going to show all of them. I wanted to point out here that at the beginning we're dealing with very the more simply some of the green chemistry principles that can more easily be integrated in. We're not trying to put them all at one time. We're trying to put a few in at a time, and then, of course, we'll reuse some of them several times so that they'll get the understanding of it and be able to grow in their understanding of using the green chemistry principles. These are the last two labs that they can do, and as you can see, by the time we get to the end of their second semester of general chemistry, we're hoping that we're trying to teach them and some of the more difficult ones to integrate in, and along with reinforcing some of the ones they've already learned. So I said that imparting a vision to think green was in some ways the most challenging part of this research, and I personally got involved in this one and trying to just figure out exactly how we could do this. And what it finally came down to was realizing that students needed to understand how important this was. It is so important. There's actually a Presidential Green Chemistry Challenge. There's awards out there. Companies and educators, professors, want to win these awards. I wanted the students to really understand that this is something that they are going to have to learn, and if they're going to go on in science or engineering, they're going to have to really know how to implement this. I wanted them to really see the importance of it, and what better way than to get them to look at the Presidential Green Chemistry Challenge website. In each of the labs, we went through and found awards that were given for something that we could relate to the experiment that they had just performed. I would like to mention that I have had 7 different students work on this project, and they did excellent work here. They developed the labs, and they knew that they had to make them use more benign materials and to be able to interest students. And they also had to come up with a teacher's manual. And what was decided by the students is that the labs were going to be very set up very much as the other way that we used in our first one, again, but also with these other sections. Now, I was the one that took their materials and put them together in a teacher's manual. They did an excellent job there, but when it came to the final format for the instruction manual, decided that what we needed to do was educate the instructors as well. Many instructors have not grown up in the knowing about green chemistry through their career, and we wanted them to educate them as well as the students, and so tried to put some points in the instructor's manual that would do this. One was including the green chemistry principles investigated at the beginning, and then an introduction that related the green chemistry principles that were taught in that chapter so that they could see what we were trying to do. We also had experimental considerations and, of course, the unified materials section with the supplies preparation alternative notes area and example answers to questions and data for the student hand-in pages, again, in a text format, not an appendix, and some Think Green information. So here is one of the first, I think it's the 3rd lab, and it's the determination of the formula of a copper supplement. In this one, we're using copper 2 glutamate instead of some of the other more hazardous ones that are used. And students are to calculate the chemical formula. We do give them the formula of a gluconate ion. We also, in this, incorporate the principles of prevention and catalysis. In a procedural overview, they use a half a gram of copper glutamate and 10 mils of 1% sodium chloride. They plate the copper onto aluminum washers, recover it, and dry it, and calculate the mass and moles of copper that they recover and determine the formula of the compound. Here is an example of what a plated aluminum washer looks like after it has the copper plated on it, and what the copper looks like after it's dried. We also have them do a pie chart where they determine the percent copper. This is used later to compare out percents copper. We relate this lab to catalyst. It is right now catalyst. They are looking at how they can reduce the amount of heavy metal within a catalyst and still have an effective catalyst. And so the percent of copper is something that's important in order to compare this out. In the Think Green, the students develop a method to determine the chemical formula for copper 2 sulfate pentahydrate. They had already done, have previously performed a lab where they determined how many waters were attached to Epsom salts. And so hopefully they would see that in this particular case, they would have to first remove the water and then be able to figure out the chemical formula. We have in there to test the procedure if time and resources permit. Again, this is an inquiry-based exercise, and we were hoping that maybe not all of the times this is said, but maybe once or twice during the semester or year that teachers would be able to give them the freedom for this lab inquiry type of an exercise. And then, of course, to evaluate the impact on the 12 principles of green chemistry. As far as the research, under the Think Green, we have some that's more of a lab inquiry and some that can be more of a research. We ask them just simply to compare the percent copper and copper glutamate and compare it to copper 2 chloride. Discuss the methods advantages. The presidential challenge, we went to the 2009 academics category and asked them to develop where copper catalyst was developed with a lower percent copper. The second example is the synthesis of sodium iron 3 EDTA. This is towards the end, the next to the last lab, where we're introducing coordination chemistry, and we are incorporating real-time analysis, solventless reactions, atom economy, and E-factor, and microwave for energy efficiency. In this one, we started out just trying different types of ferric compounds to use and ended up deciding on ferric ammonium sulfate. We checked our results by IR, and this is just showing how they compared to some purchased material. In this procedure, we actually have 2 reactions. The first one's a titration that uses EDTA, and at the beginning, and they do this in a small amount, and I'll show you in the next slide what this looks like. But they see that the synthesis completion correlates to a pH increase, and then they actually use are introduced to real-time analysis. The second procedure they do is a solventless procedure, and it involves a ferric acetate intermediate and a microwave. And the students at the end compare their atom economies, E-factors, percent yields, and energy efficiencies. Here is what the titration looks like. Again, they use just a small amount at the very beginning, and a salicylic acid indicator. They also have a pH meter in there. And what we want them to see is that the pH decreases at first, but once they have made all the compound they're going to make, the pH goes up. They then do it with larger amounts using only the pH meter and no indicator, because the indicator, of course, adds a contaminant that has to be removed. As far as the solventless, they actually use beakers to do this. We originally started with mortar and pestles. As you can see, it starts out with fairly white powders, and over a very short period of time it turns into a very brilliantly reddish tinged or reddish colored ferric acetate intermediate. As far as the results on this, what they will learn is the atom economy is better with the titration, but the E factor is better with the solventless. In the titration, they end up having to use a hot plate, and it takes 27 minutes to concentrate the solution down, where with the solventless, they do, in the second part of the solventless experiment synthesis, they do have to add a small amount of solvent, but it's small enough that they can heat it in a microwave to grow their crystals, and it only takes 1.5 minutes. So this, of course, is increasing the energy efficiency. The Think Green on this synthesis is all just research in this case. We did not have the inquiry exercise, and they can research a coordination compound of their choice, solvent purification or disposal, green chemistry metrics or microwave reactors, and of course that would be up to the instructor to either allow them to choose one of these topics to write a brief report on, or to assign a particular one. The Presidential Green Chemistry Challenge in this one is, again, 2009, although I guarantee we do use other years. But it went to Eastman Chemical Company for their solvent-free process that they're using to produce esters, again, relating that solvent-free is something that is being used by industry. So in conclusion, we have managed to complete a green chemistry lab manual for high school and introductory college chemistry. We have also completed the instructor's manuals and have worked with eScience labs to produce, so that in order to that they could use these labs in a kit. And we have made the manual available for the high school, introductory high school, through our website, www.greenchemistrylabs.com. As far as general and AP, we have completed the Green Chemistry Laboratory Manual for general chemistry along with an instructor manual, and have worked with eScience Lab for them, giving them materials that they could develop into a kit for this level as well. And this manual is available through CRC Press, Taylor and Francis Group, of course on Amazon as well. Our future goals, we're wanting to incorporate green chemistry education into introductory manuals. I'm wanting to revise the first manual we did and put some appropriate material for students to learn about green chemistry at this level. We also want to complete and make available the introductory college student and instructors manuals that we have completed the students one, but we never have made that available. And I would like to incorporate more green chemistry education into that manual as well. Again, we're going to continue to monitor the results and make indicated improvements and develop additional green labs and demonstrations, and of course continue to promote the use of green chemistry labs through presentations, in-services, and workshops. I have so many people to acknowledge from Union University. I have our chair, Dr. Randy Johnston, my colleague, Dr. Marlon Newhouse, and Mr. Guiley Wright and Cam Tracy, who helped us develop out the website and helps us keep it going. CRC Press and Hillary LeFeaux and Judith Simon and Jill Jurgensen, they've just been wonderful to work with. Of course, eScience Labs, they've been wonderful to work with as well. And we were able to get a few grants through the efforts of, TEGL grants through the efforts of Dr. Matt Lunsford. And of course, I could not have done this without the research students who spent many, many hours developing these labs out. And I've been very grateful to have such wonderful research students to work with. And again, I would like to thank you, and I would like to thank Amy for inviting me to make this presentation.
Wonderful. Thank you so much, Sally. That was fantastic. There's a lot of information there, and I know, this is near and dear to our hearts here at Beyond Benign as well. So it's just fantastic what you've been able to do. So thank you so much for sharing that with us. And so we do have a few questions that have come in here as you've been talking. We have the first one I'm going to read to you here. Have there been any research studies done on how these labs affect student interest in chemistry or science in general?
That's a great question, and I wish there has been. I have heard from high school teachers some that the other work obviously is just too new to really have any data on it, but that students have enjoyed the labs, and it has for some of them it has piqued interest, but absolutely no hard data. I have absolutely no hard data on it, and I wish I could say we did, but we just don't.
Okay. Yeah, I know. I was trying to think if I knew of any too, but I'm with you on that one. Okay, so our next one is, have there been any concerns from colleges about students coming in without experiences doing the classical types of laboratories?
I'm assuming that they're talking about for the web-based kits. And I've heard that concern as well. And with the kits and what they do, I wanted to be sure that the students in our web-based materials that we did, that they would be able to actually have larger amounts and go through procedures that are as typical as we could get. There is a balance there, and actually use beakers and flasks and burettes, and so that was very important to me. I didn't want it to just be test tube chemistry. I felt that was just going through the motions, but they were just dropping drops of this and drops of that and seeing a color change, and I wanted them to actually have more of a science experiment, even if it was at their house or at some kind of a setting. So I was concerned about it. We here at Union get many homeschooled students, and when they come in, they are wonderful students, and they do a very good job of it. I understand that there are some school districts as well who have students that need these types of kits in order to, and for some reason they are homebound, and so as far as my own personal experience in dealing with homeschool students, I really haven't seen that as a problem. Admittedly, they may have to learn how to light a Bunsen burner or some other things, but they seem to be able to adapt and do quite well once they're put into a traditional lab on a college campus.
Great. Yeah, that's great. And just very briefly, Esther Beaumire, you're the winner of the book, so we'll be sending you a note. Sorry if I mispronounced your last name. You can correct me in my in the email as well. So another question: once students go through your program, have you noticed a change in attitude towards the study of chemistry? So I think you can probably answer that regarding the program in a number of different ways. So either students who have used the resources that you've developed, or yeah.
Right. What I have seen is that as I have incorporated more and more green chemistry education in my classes that I teach, that the students, it takes a little while, but then they get it. And once they get it, especially the ones, and once they get it, they become very excited about it. It took a while to really get it figured out in my mind how to get them as excited about it as I was. And again, using the Presidential Green Chemistry Challenge and and having them work through and try to come up with ways to develop greener methods and seeing that they could do it, they could make improvements, seems to have also excites them, and they will take it with them as they continue on in whatever field they choose. Out of this, we have of the students that were there, I think 5 of them have gone on to high school teaching, and so they are interested in using green labs, obviously, and so they do change their attitudes and start thinking, how can we do this in a more green manner?
That's fantastic. That's great. I love it that they're getting out there and teaching too. Are you doing any summer workshops?
I haven't been asked. If I'm asked, I would definitely consider it. I haven't really put it out, and I'm open to do workshops. I just, as people hear about me, I guess I occasionally get invited to one. I just did one up in at Youngstown State University, and over in December, end of December. So if somebody would wants me to do a workshop, I would love to do one, and just contact me, and we can see if we can work something out.
That's awesome. Well, I'll be following up with you on that, because we do workshops all the time, so we'd love to have you join if possible.
That would be great.
Is the AP lab manual available yet? I assume that's the same, your intro.
It's the same as our general chemistry laboratory manual. Let's face it, AP, what they are trying to do and trying to take is the same as it's the replacement, so to speak, for general chemistry.
Yeah, and I just put that web straight to the CRC Press in the chat box for person who answered that question too, or asked that question as well. And this looks like our last question, which we're coming right up against this perfect timing here. Are you aware of the Arizona State University Green Labs program? Would you be interested in possibly collaborating on adding elements of your manual to the Green Labs checklist application? And this person works for the program and found this very interesting. So if there's interest, I can connect you guys.
I would be interested, and you could either connect me, or they could email me or call me, either one.
Yeah.
And
awesome.
I think you have our phone number that you could let them have, and I'm very interested in collaboration.
Awesome. That's perfect. Well, thank you again, Sally. This has been wonderful and really informative to hear all about all the wonderful work that you've been doing in green chemistry. You know, I love that you've got this focus on getting students to think early about thinking green. So that's just fantastic. So thank you, everyone, for joining in on the webinar. Please join us next time, April 26th. We'll be highlighting the Environmental and Green Chemistry Master's course at George Washington University. So we have 2 faculty there who will be joining us on that, and they'll be talking about some of their courses, including a new sustainable design course that incorporates toxicology into the synthetic design process. So we're very excited about that as well. And as always, all of our recordings are posted on the link that you see here, and they're posted by the end of the day today. So thank you so much, and we look forward to talking with you next time.